we have, as you will see, some other important tools, and essentially what's happened here is we would want to prove this using a ping-pong argument to show two different directions, like we saw in class last time. So we've proven this direction already, so we'll look at the opposite direction in class, and maybe we'll try another alternate equational style proof to see that as well. We can also do this with or and as well. Finally, in this section, we have a number of other examples of different absolute theorems in predicate logic. So we aren't necessarily going to use these different examples as tools in our toolbox, although you certainly can. But I don't find them always that useful in terms of being able to prove other things. They're going to be helpful for you to practice your proofs, for sure, and also there are certain properties in mathematics that we need to establish and that are used when you practice in a particular area of mathematics. So we won't go through these in detail, but each of them is explained in the notes completely. And I recommend that you try and practice your proofs by trying to prove each of these statements and then checking your proofs at the end. So we have a number of different examples here. This notation is good. It's more readable than this one, so I apologize about the slides and the form that they're in, but in the notes it's more clear, and in the textbook I think they use this more complicated notation. So these other translations will be more helpful. Okay, so a number of other different properties, different examples of absolute theorems that we need, but that we won't necessarily use in any proofs. One theorem that is really helpful is the dummy renaming theorem, particularly for the universal quantifier. So the dummy renaming theorem says, if Z does not occur in A, neither free nor bound, so Z is not in A at all, so essentially I guess you could think of Z being fresh with respect to A, then quantifying over X in A is equivalent to quantifying over Z, where instead of writing the x's in A, so wherever x appears in A, we replace it with Z. Remember that we would perform this substitution first, because substitution always has highest priority, and then apply the quantifier. So what is this really saying? It's telling us that, so what do we mean by dummy renaming? So remember that all of these variables are simply variables. They're just placeholders for something. So saying for all x is essentially the same as saying for all z, so long as wherever you see an x in A, you replace it with z. And here we don't have any confusion because z does not occur in A at all, so it's fresh. So that means we can replace every occurrence of x by z, and A is still the same A, and then we quantify over a different variable. So we're simply changing the variable we want to quantify over in our formula. Now you may ask, what's the strength of this? Why do we care? Well, here, notice the big strength is that now we don't have to worry about any capture. Dummy renaming says, well, if I'm trying to do substitution and I'm going to put a free x into my A and make it bound here, then how about I first change the variable I'm quantifying over so that I can substitute in this different variable x into A and not have to worry about it becoming bound. I want to change x being the bound variable here to z. So that's the strength of dummy renaming, and of course this is a common practice. We often do a change of variable in a number of different mathematics applications, such as when you're taking infinite sums or other kinds of sums, or using summation notation. Oftentimes we change a variable to get it to look like what we want, and because it's a variable, we're free to do that. Of course, as we're starting to now introduce this existential quantifier, we have the dual, that's what we call it when we're talking about the equivalent with this new quantifier here. So the same statement occurs.